Hi, this is the presentation for Chapter 9 about completing quantitative data analysis. The topics that I'll cover here are analyzing quantitative data. The textbook authors assume that you already have some basic knowledge of statistics. They also say in several places in the text that this course and this text are not going to be sufficient for you to complete a research project. So this is just to give you a background in research and how to read research studies. So that's certainly true for this portion. So the aims of this chapter are to get you to be a little bit familiar with the ways that researchers who are doing quantitative studies analyze their data, and it mostly has to do with using statistical tests. There's certainly some statistical vocabulary to learn. So if this is hard for you, you're in good company. It's hard for me. I tried to explain it to you in that within those modest objectives, that you would get to know something more about the vocabulary, just like for qualitative analysis. Although I know about that because that's what I do. So the aims here are just to get you familiar with the language. So we'll take a look at the types of variables. We'll refresh on what variables are, what they do, and which type of statistical tests that you can use. Even statisticians use cheat sheets. So don't for a minute think that you're going to memorize automatically which test is best under which conditions. There's no need to do that. And that kind of familiarity with statistical testing only comes from experience using the tests. So we'll take a look at descriptive statistics and then the test for calculating inferential statistics. And an inference is an informed guess, a guess about something based on evidence, though. It's not just a supposition, it's not an intuition, it's a guess about something based on evidence. And then going on to some of the most common statistical tests, how to deal with missing or incomplete, your authors call it out of range values. So for example, I was participating in a research study on osteoarthritis, and part of the data being collected was a blood sample. Well, the woman trying to draw blood from me had an awful time, tried both arms, felt like I was going to faint, finally said, I'm done. So whether or not they got enough, I would guess that would be an incomplete data. So whatever they're going to say about me as a subject, they may not be able to say if whatever they're finding in the blood draw is necessary for that relationship to be established. So what do you do about that? And the answer is that you're responsible for that, and you can still use the other data and still include that participant, myself, in the evidence from which you can make an inference about, for example, lifestyle and range of motion, right? So they were testing the range of motion of my knees and observed that it's typically only yogis' knees move that way, right? So maybe they'll be able to talk about that in the study. We'll take a look at reliability and validity. It's kind of funny that we had the conversation in the last presentation about reliability and validity as alternative constructs to represent ideas that were established by traditional scientific researchers or those using quantitative methods. So it's a little bit backwards. So here we have the definitions as they were meant to be used in research. And then technology that supports quantitative data analysis. This book doesn't go too far into SPSS, and I've done my best to give you resources for taking a look at the software that I think will be helpful. You do have access to SPSS on the Computer Lab computers, and you can go through our technology services website if you want to purchase a discounted version, discounted copy for yourself to use of SPSS. But the good news is you don't have to use SPSS. You can use Excel pretty well for for reasons of understanding in this course what the tests are. So I encourage you to play around with that a little bit. I've played around with Excel a little bit, and I've provided some data for you to use if you want to explore. But again, the idea is that we're trying to understand what researchers do with their data when they're analyzing it with their quantitative data. Okay, enough of the introduction. So the cartoons are going to reflect my sympathies for people who are more qualitatively inclined and somewhat baffled by quantitative data. And at the same time, I'll critique and poke fun at quantitative research a little bit. It can handle it. It's the dominant research paradigm, right? It's the old man in the club, so of researchers, of research paradigms. So we can make fun of it a little bit. All right. So just like with qualitative research, actually, when you do quantitative data analysis, you're going to take a cyclical approach. So that means we use the term iterative in qualitative research, which means that there is going to be, it's circular, but then there has some third dimension to it too. Here, cyclical is, I guess, likened to linear, except that you just begin over again. So here you go. You prepare the database, you become familiar with the data set, you calculate the descriptive statistics, and then set and run additional inferential statistics. And then you continue on with different phases of the research if you, unless you're done, maybe one cycle and you're done. But if you have a continuing phases of collecting and analyzing data, then you're going to go in a circle. Okay, preparing your data sets. So the important thing is, because you're going to have to write about it, describe it to people, and keep track of things yourself, is to have a plan for structuring your data set. It's kind of easy if you're using some electronic survey, because that's going to not just collect your data for you, but be able to display it in a pretty nifty kind of way. And I started using a more advanced version of SurveyMonkey recently and realized the things that it could do. So just like with qualitative research data, you want to know where you're going to keep your survey data, where you're going to keep your student information system, where you're going to keep your assessment scores, and et cetera. So a nice Excel spreadsheet is fine for that. Here's some terms to think about. Any element in your data set to which you have assigned some value or meaning that is relevant to your study is going to be considered a variable. And that's going to, remember we talk about either dependent or independent variables, but then there are extraneous variables too, maybe things that you're not actually testing for, but you want to be aware of. And sometimes that can be demographic data, although that does sometimes get tested, included in the experimental or correlational data. But sometimes it might be for teachers' years in the profession, or it might be extra professional development in a particular content area, or in an ancillary area that isn't part of the study but is a variable nonetheless. So if that's data that you've collected, you want to organize that in your nice columns. And remember, just like with qualitative data, the highest ethical standard is to keep your original names of participants and sites de-identified when you have all the data set up, and so that only the primary investigator can actually see the names attached to the de-identifier, which whether it's a pseudonym or a number, usually a number when you're using quantitative data sets, but maybe it's like a numeric, an alphanumeric. Okay, assignments just mean the value that you give to your variable. So in a Likert scale, that could be something like agree equals 5, or instances of how frequently you do something, never would be 1, or I guess actually never would probably be 0, right? So you prepare your data set then for analysis. First, by standardizing your values, so ensuring that all variables with the same values are treated similarly. So maybe all frequencies, how often someone does something, are going to be represented in percentages, and then all A grades are going to be assigned 4.0, all Bs assigned 3.0, and so on. Have a code book so that you know what you've done. You can go back to it. Take a look at page 192, table 9.1 for an example of a code book. And this is just an inventory of your variables and their respective values. And then key punching is just another way of saying entering values from a paper survey or some other format. Maybe you don't have a program that imports electronic data. Maybe you're going to have to type that in. And I've already said SurveyMonkey is going to take your data as long as you have assignments to it, right? Your qualitative or open-ended responses. If you've given, your closed-ended responses, if you've given a number to it, it can generate tables for you, and bar graphs and charts, and very nice. So there's your code book, an example there of assignments. And these are arbitrary assignments, which is why you should keep a code, because you're not going to look at these assignments later on and think, oh yeah, that makes sense. So, if you look at something like race or ethnicity, are you going to remember that 3 is Hispanic, right? Maybe not. All right, so a part of your code book, your spreadsheet, right, is you're going to keep track of the identifying the different kinds of variables. So what are they? And remember from chapter 6, we took a look at independent variables and what they do. Those are your predictor variables. Those are the things that are the tests, right? The interventions. And then the dependent variable is the outcome variable. So if you're testing a reading program as an intervention, that would be your independent variable. And you're looking at reading comprehension of the students who use the program, that would be your dependent variable. The dependent variable depends on the independent variable. Again, chapter 6. And then there's extraneous and confounding variables. So like I said before, any other variable that's not the independent variable, but could impact the dependent variable. So here, for example, anything from the temperature in the room to teacher-student relationships, family characteristics of students, things that aren't being measured, but probably have some influence on the relationship between the independent and dependent variable. And then categorical measures, right? So some more language to learn. Categorical measures broadly refer to categories. So here we go. with some new language, binary variables, the either or. I don't so much like, and I don't know that it's, we're kind of moving away from using male female as a dichotomy anymore, even though you see that as an example in several places in this text. So I like something more absolutely concrete and politically neutral. So pregnant or not pregnant, right? You can't be a little bit pregnant. You're just pregnant or not pregnant. Nominal variables have 3 or more categories. So that's a binary is always 2. When you get to 3 or more, it becomes nominal, right? So maybe gender is more appropriately referred to as nominal, male, female, and intersex, or genderqueer, or whatever option for none of the either two. So ethnicity could be one of these, age could be one of these. Ordinal variables we saw before, having a defined order for second, third, and that could be, sections, it could be participants, it could be quintiles. So, however, whatever you can rank that way is called ordinal. And then continuous variables are those things that have a value between a minimum and a maximum. So the reason age isn't here is because there's no zero age. Test scores and height. Continuous, well, there's no zero in height either. So if you have a minimum and maximum, let's just use the language that's presented in the textbook, then that can be a continuous variable. So in other words, you can, the idea is it's always going to increase, although with test scores, it could certainly decrease as well. And then 2 kinds of continuous variables, the interval variable. Here's the ones that don't have the absolute zero, and then a ratio variable. That scores are based on some kind of scale. So it's not necessarily starts at 0 and ends at infinity. The ACT, for example, scores are based on a scale. Just the important part is learning the vocabulary enough so that you can use it in a meaningful way. So, and you can understand how the authors of the research studies that you're reading have used these terms, right? So you're not so confused if they're referring to something as a continuous variable. All right, descriptive statistics. This is something that just about anybody can do, and these include things like frequencies and tendencies. And so if you're doing a qualitative case study and you do decide to include some quantitative data, chances are it's going to be frequency data. Patterns, trends, and frequencies. A frequency is just a simple count. So referred to the number of times some things happen, the number of times people have shown up for a training, the number of times people have used a skill that you taught them. So you can use frequencies to identify baseline patterns. So for example, participants include 560 students, 84 with IEPs, that's 15%, 498 who receive free or reduced lunch, and that's 89%. So if you're just describing your population before anything has been manipulated, anyone has been assigned, you're just describing. And then you can also use frequencies to identify trends. So for example, in a study I did, behavioral specialists report more incidents than do gym teachers on average, 10 a week versus 0.75 behavior referrals a week for classroom teachers. Or you can say on average, parents give their local schools a B+. And that seems to be a pretty resilient finding in that in survey after survey of parents' feelings about their own local schools, they all think that they're doing pretty darn well, despite what, completely unrelated to how they feel about the nation's public schools as a whole. All right, measures of central tendency. So these are things that you'll probably remember from math at some time in your, I don't know, upper elementary. When do we learn these things? Averages. A little different, right? 3 different kinds of ways to talk about averages. So the mean is the actual average of all the scores and the values. So when we say mean, we mean what people commonly mean when they say average. So average and mean are the same thing. But the median is the midpoint, and it might not be the average. It might be, something different. So medium home prices, you hear things like that. That's not the average. That's the number in between the distribution of scores and values. And so it might be more meaningful to know the mean if you're more interested in getting an idea of what throw this off. So if you have houses out there that are absolutely free and those that are several $1,000,000, then your median is going to be thrown off. And then the most frequently occurring score. So on, what is, most people are going to eat at least 3 meals a day, right? Or let's just say 3 meals a day. So if you're asking people how many meals they eat a day, then in most cases, most people are reporting 3. That's the number that keeps coming up for you. And then moving on to a little bit more complex, a measure of variability. And so how far the scores move away from that average, from that middle. So the measure of variability just refers to the spread of the scores or values. So if you plot them all out, what is the range, right? And how are they distributed? And the range is just the difference between the lowest and the highest score or value. So 1 to 10, 1 to 100, whatever you have. So, and where are those plotted? So, like I said, if you're asking somebody about number of meals eaten in a day on 1 to 10, you're going to have probably all of them grouped around 3. If you're talking about the US, if you look at variance, here's another term that means the amount of spread across the scores. So how far the scores are from each other. Population variance means the spread of all scores for all members of a given group, and then sample variance means the spread of the scores for just a subset of the members of a given group. And those might be meaningful depending on what you want to talk about. And then the standard deviation is technically the square root of the variance of a set of scores, but more meaningfully, it's one expected expected to move away from the mean. So this is more meaningful with images, I suppose. And if you look at pages 196 and 197 in your text, you'll see figures 9.4 and 9.3. And I sort of reversed the order there so that you can see the normal distribution there. So most scores are going to fall then in the middle, and then I said, when you're talking about standard deviations, one in either direction might be expected. The ones on the tails are things that that we don't expect. And then if you look at the image on the right, you can see that there are scores or values that are plotted in one direction or the other, leaning away from the average. So negatively skewed are scores that are typically above the mean, above the average, and thus score further from the y-axis. So that's the vertical line. And then positively skewed scores are they're typically below the mean and thus closer to the y-axis. If you take a look at graphing the data, take a look at the ways that you can do that. The pie chart, which is figure 9.5, is just what it looks like, right? A piece of pie. And so that's a good representation of about the differences between males and females. And again, we should have some representation of anyone who doesn't identify as either or. Chances are this is representing data that's marked in a data set. If you were to ask a population about their gender, you probably have depending on that's figure 9.6. So you can if you're taking a look at, you might see this when you look at a average temperatures for a particular area in the months along the bottom there, and then the temperatures along the side. That's where I typically see a bar graph. And then a line graph, so you see these in trends, business trends, stock market, things like that. So inferential statistics. Now, take a look at Module 3 at the supplemental materials there and little cheat sheets for you. And this is where things get complicated for me. Let's go back one. Okay. Inferential statistics are just tests used to make guesses based on evidence. So that's all that means. But what quantitative researchers do with these are make inferences about the population as a whole based on a sample, predict how variables will interact or relate to one another. So this is good news when we're talking about whether or not we should continue funding a program. And also assess the degree to which these interactions predict outcomes. So if we're going to try to be guessing on a need by studying some past trends. And then hypothesis testing is usually what you're all about when you're analyzing your quantitative data. What you're trying to do is decide whether or not there is going to be no influence or is associated with some kind of change in the dependent variable. And you may not see the null hypothesis written out. You might just see the alternative hypothesis written out. That's mostly what readers are interested in. Most people aren't going to write a study based on a test um, of the null hypothesis because nothing happened. The exception there would be if someone is testing someone else's results, and maybe in practice and experience, it really doesn't seem like there is an effect. So maybe they're testing that and they really are looking to support the null hypothesis. And that's important for science. The idea of science is that we always accept something as tentative until more evidence comes along. And it's the responsibility of scientists to try to find that more information. So hypotheses are being tested all the time, and the results of people's research is being tested all the time, and that's the expectation of a scientific community. And that should be the expectation of researchers everywhere, more so for people who are making more strongly asserting their truth claims. Not a term that you hear in quantitative research, but it's meaningful to think about. If you are making a strong statement about relationship between variables, then it's your responsibility to be open to being wrong about that and to um, continue to look for evidence that is going to modify your position on something. So when we talk about a hypothesis, whether we're going to support no relationship or whether we find that, yes, in fact, there is a relationship there, we always want to talk about how sure are we that there is a relationship? How sure are we that these associations aren't by chance? And what's considered acceptable is about 5% chance. So your significance level, also known as the alpha level, should be 0.5. And that's why you see that as the marker of significance. So significant differences are those that calculate to 0.5 or less chance of happening randomly, right, with no association. And this means that you are very sure that the difference is real, right? So that it didn't happen by a fluke. But it doesn't mean the difference is large or important. It just means significant. And you can read more about significance from StatPack. To get the link for these presentations, I've tried to write this into the notes on the on our Western course base, but you'll have to download the original presentations so that you can get the hyperlinks, because they don't work from within the YouTube video. But I think that's something that's often confusing for lay readers, is that they read that results are significant and they take that with the common meaning of being important. But that's not exactly what that means. So calculating inferential statistics. So it has to do with, these have to do with increasing patterns. So I thought this was funny. The cartoon says, if she loves you more each and every day, by linear regression, she hated you before you met, right? So something increases each and every day implies that there was a 0 point and even a point of negativity in the past. So inferential statistics always has to do with choosing the right test, because you're going to make statements based on evidence, and the evidence is going to come from your data, and the way you're going to be able to make statements about it is by doing tests. And the good news is you won't be doing these by hand. You'll probably be using Excel, or maybe some of you will use SPSS. Maybe some of you have already. So again, reminder, you're identifying your independent variables and your dependent variables. And this is how you start deciding what tests you're going to have. You have to count how many of each you have. Are they continuous, right? Either ratio or interval, or are they categorical, either nominal or ordinal? Are they parametric or non-parametric? That just means normally distributed. Um, and usually if you have a non-normally distributed set of data, then you're going to use a different statistical test. So that's why it's important to take a look at whether you have a normal distribution or not. So remember that graph that had the high point in the middle, right, of the normal graph. Ask yourself, will you compare or relate groups, and which ones? And will you attempt to control for any extraneous factors? So remember, all the chart that you have, you can make those decisions. And whether you answer yes or no, or how many, or what category, then you'll be able to know what test to use. And a few of the most common statistical tests. Again, see the common statistical tests explained in Module 3. And here you go. So these authors actually pull from Creswell, the guide that I use for my qualitative research methods. Here's a test that he generated. It's table 9.2 in your texts. Here's the different tests that you can use, some common tests, depending on purpose, number of independent variables, dependent variables, type of independent variable, type of dependent variable, and whether your data is evenly distributed or not. Here's the test that these authors focus on here. And again, you don't get a lot from these, so you're required to take a look at these if you're interested in using these tests more deeply later on. And I've provided as much as I can by way of simple explanation, right? I don't want to get you buried with these things, but my measure for judging whether or not you got a link on this was whether or not the information was comprehensible to me. And really, I'm someone who does not use quantitative data, but a lot of the field that I'm interested in, mindfulness in schools, does include randomized control trials. So it's important for me to understand minimally what my colleagues are doing and what it means when they're using tests to make inferences based on data they're collecting in the same area that I'm interested in collecting stories and the experience of participants and observations in. So here we go, the simplest test, the t-test. You're just comparing scores here. Comparing scores or values from two groups, right? If you have more than two, you're going to move on. So this is just two groups, males and females test scores. The test scores of third graders at Hamilton and third graders at Jane Addams, right? Just two groups. And you want to know if there is a significant difference, right? If that means if there's a difference that is that exists there with less than 5% chance of there being a fluke, right, in the relationship. So that's what significance means. ANOVA means analysis of variance, ANOVA. This is a test that you're going to use to compare two or more groups. So maybe you have reading scores among 4 groups, and this is just a more complicated statistical test. So again, already happy, right, that you're going to have Excel or SPSS to tell you whether there's significant differences between two groups and among more than 3 groups, 3 or more. The Pearson's correlation, or Pearson's R, sometimes written as a little r. I think it's also slanted off to the side too, indicates whether there's a relationship between the two variables. And this is the primary test to use in correlational studies. Maybe it's the only test you're going to use if you just want to find out whether there is a relationship between two variables. And you're going to get a score of somewhere between positive 1.00 to negative 1.00. So if there is a a relationship on either side. There could be a relationship that's positive, so as one is present, the other increases, or negative, as one is present, the other decreases. So with number, the amount of or the level of family affluence is going to be positively correlated with student academic success, and the number of adverse childhood events is going to be negatively correlated with student success. Simple linear regression or multiple regression. So one of the other simple is going to predict the value of an independent variable from the known values of one or more dependent variable. So maybe the number of hours of reading instruction needed for a passing score. You can do a regression to predict that. You can only do this if your independent and dependent variable are continuous and the data are parametric. If not, you're going to be using another test. So the chi-square seeks to determine whether there's a statistically significant differences among data that are reported in the form of frequency counts, percentages, or proportion. So it's going to indicate for you whether there is a difference between the observed and expected values. Is there a difference between the growth that you expect and the growth that is indicated on a test score? It can answer yes and no for you, but it can't tell you the strength of the relationship. So for that, you might have to use a more sophisticated statistical test. But if you just want to know if there is a significant difference in projections versus actual scores, then you can use that test. Okay, identifying missing or incomplete values. I thought this is funny. At first, you think, well, what do you mean you would have missing data, and what do you do? You can't work with that, right? Well, so it depends on how large your data set is. For very large data sets, it's probably not going to affect you so much if you have some scores that are missing or some scores that are incomplete. Okay. So I just finished saying that if you have a large enough data set, some missing data is going to be okay, but it's always a threat to your ability to make some kind of claim about your hypothesis. It's always going to threaten the confidence that you're going to have in making a statement about what you find from your data. But still, the authors of this textbook say it's acceptable to go ahead and run your tests and present your results with up to 15% of your values missing or incomplete. And I guess that depends on how you represent what you've done, as long as you're honest and upfront about what happened to the data, and that you are only making claims about relationships between data that you have values for. I think that's good. I would think that it's more common, though, to expect that you would go ahead running your tests with just up to 5% of missing data. But if you're going to be doing research as part of a project for a degree program, that's something that you and your committee will have to talk about. But I think that it's more common to settle on 5% as being acceptable. And so I suppose it would be, though, okay to go ahead and make statements about relationships where you do have data values present. So, for example, in the study where I'm participating, They're collecting lots of different kinds of data from all of the participants, and some of it's going to be missing. So another thing I'm doing is wearing a monitor around my back. It's supposed to measure my activity, but as I was doing yoga today, I noticed it was moving all around. So I don't know that that's probably going to be independent data for this participant. So still, they can still talk about all of the tests that I did for them with range of motion and strength and speed, and they're taking X-rays and MRIs and CT scans of my knees. So all of that is good data. So they don't have maybe the information from the blood, and they probably aren't going to get good data from this monitor, but they'll still be able to run tests on variables from my data for the values that are complete. So, and it's going to be way more than 95%. So what do you do then? So how do you go about working with incomplete data? So you can start deleting some participants. You can delete entire records from the data set. And so if you have large samples, you could do that. So if I had lots of incomplete data, maybe they would just say, well, we just can't use you as a participant anymore. Or you can do pairwise deletion. So you're excluding incomplete or missing variables just from the analysis where the variables are meaningful. So if age is missing, you don't use that in analysis where you're making a statement about age. Lastly, there's mean imputation. So the mean score is entered in place of the missing scores or values. That's surprising to me, for example. And so I understand, with a large data set, and it might be acceptable to say, well, we see that we have 10 different tests or maybe 100 different tests for this one participant, but scores on 10 are missing. So we're just going to take the average of all her test scores and enter those. Or maybe it's you're going to take a look at the average if you just have one set of test scores, but you have 100 participants. Instead of treating those values as listwise deletions, you might include the mean score of the other results there. And however you decide to do that, you're going to have to be able to describe what you did, right? Tell the tale of how you dealt with this data and why it was meaningful for you. And then that is going to be a reason for you to tone down the claims that you have to make, depending on how large the amount of missing data was. And again, we go back to acceptable. And yeah, I would guess that 5% or less would be acceptable. Okay, reliability and validity. So in quantitative research, in traditional scientific research, this is where these terms come from. And then if we use them in qualitative research, it's because we are trying to talk about parallel constructs, but this is where they live. I like the bullseyes. I found images of these just about everywhere. And I'm someone who consistently has to look up reliability and validity and how they're used in traditional scientific research and in quantitative studies, because I don't use these terms this way. So I always get confused. But you can look at reliability. The bullseye, the archer's always hitting the same spot. So no matter what, this archer hits the same spot. So that's reliable, but he's not actually hitting the spot that he wants to, so it's not valid. So his measure, imagine the shooting of the arrow as a measure. It's not hitting its target. It's not measuring what it's meant to. So again, you can see that the far right there is unreliable, and you don't know where it's going to score, and it's also invalid. And it's going to be one of the reasons it's not going to be valid is because it is unreliable. So we don't know where the score is going to go, and that's going to be one of the threats to validity. But here you see reliable and valid. So um, the archer is always making his mark. The test is always measuring what it's supposed to in a reliable way. So here we go then. So this might make more sense to you, hopefully. Reliability has to do with consistency. It's the consistency of the measure, or the degree to which your measure is replicable across different administrations. The test is going to be reliable if it always is producing the same outcome. You're always going to get the same results with this test, or similar, right? There's a degree of error that's involved when you're using human subjects, of course, right? So remember, the biological model applied to human research, social science research. There's always a question about whether it's applicable to use this language when human beings aren't the simple organisms, and there's always going to be extraneous factors that are going to interfere with reliability. So maybe you have a perfectly good test, but you're never going to be able to have absolute confidence that you're going to get the same result from the same measure when you're talking about human beings. So validity, the degree to which the inferences drawn from a score is accurate, and that just means, is this test really getting at what it's supposed to get at? Are we measuring something different altogether? So, for example, the relationship between family affluence and student achievement is very, very strong, but sometimes we are actually measuring that effect when we think we're measuring the influence of the number of hours spent with a computerized reading program, or we're issuing the SAT, and originally it was supposed to predict student success in college, and we now no longer even imagine that that's going to happen. So consistently, has it not actually done its job in being able to predict how well someone's going to do? But what it is still reliably correlated with is family affluence, so much so that we say that that's what it is. It's a measure of family affluence. So different kinds of validities of your test. Construct validity, so the congruence between your ideas and the way that you measure them. So, is this actually, do these match? The content validity, the degree to which the test measures what it intends to measure. That's mostly what we think of when we use the term validity. Criterion validity, the extent to which a test score accurately reflects some type of performance indicator. So is there a match there between your test score and the ability to read fluently, right? Or is there a match there? Sample validity, the extent to which the sample represents the population. So at any point along there where there is a mismatch, then you're going to have a threat to validity. And there's ways to test for threats to reliability and validity. Reliability is a little bit easier. Validity is, you have to think a little bit more, especially about your sample. It has to do with representation and random assignment. With your construct validity, you have to go back to your hypothesis, your assumptions, your theoretical frame. And if you follow this link, you'll have to download the PowerPoint to get to this link here, but a professor from UNI includes some pretty easy to understand tests for reliability and validity. And finally, I have to refer you once again back to Module 3 to look at the resources for the technology that supports quantitative data analysis. And here is just a screenshot of what SPSS looks like. So it's not, when I was studying social sciences in the late 90s, we worked on SPSS before it had this very Windows friendly interface. So this looks to me a lot more like Excel than it used to. So SPSS isn't as difficult as it used to be, and it's going to import data from all kinds of spreadsheet systems. So maybe use, I don't know, SurveyMonkey might import directly to SPSS. It certainly imports to Excel or any comma delineated system. But if your questionnaire doesn't upload to SPSS, you can go to Excel and then upload data from Excel, certainly. And we're done.